Chapter 2. Atoms, elements, molecules. And I mentioned this some time ago. When we talk about atoms, that's an individual particle, and we talk about elements, that's a whole lot of particles, a whole lot of atoms. When we talk about molecules, that's an independent entity, whereas compounds semantically refers to a whole lot of molecules. Now, please keep in mind as we go through here the definitions of elements and molecules. And it's important that you remember elements are the smallest entity of a substance. And they are characterized, they cannot be broken down. Okay, so that is a distinctive difference between these particles called elements and molecules, which are also substances, but these can be broken down. I'm not going to write it all out again. Giving two or more parts and the context. So as this evolves, that idea needs to stay in the back of your mind that, well, we'll start out with elements, and when we talk about breaking down, we're talking about destroying the nucleus. And if you destroy the nucleus for whatever reason, you will change the element into something else, and that's not the context of this chapter. Changes do occur, but they occur in the valence level of the element. All chemistry takes place at the valence level, and that's either through the gain or loss of electrons, which we will talk about shortly in ions. Anyway, study of organization of chemistry is really the classification of matter. And as we've said before, matter is anything having weight and occupying space. Yeah, that's everything. So studying everything at one time is a little difficult. Appreciate that. So what science has done is divided into mixtures and substances. Mixtures are homogeneous and heterogeneous. Substances are divided into elements and compounds. And when we talk about the general nature of mixtures, we say these are physical in nature. That is, they are mixtures that can be separated by a physical process. And solutions can be separated by a distillation process. You heat it, and if you get to the boiling point of the solvent will evaporate and leave the solute, which was dissolved, behind. distillation apparatus. On the side for the substance, these are chemical in nature. And establish the chemical nature of substances and compounds based on interactions called chemical reactions. And we go from there. Now, we've already talked about the essence of how these interact and stuff like that, so we're going to jump right in. One of the things you want to keep in mind as I go through this is how the subject will evolve. It evolves from the most simple to the more complex, and that's based upon Dalton's atomic theory. And so we're going to look at the structure of the atom first, and then what are elements, molecules, and compounds. And after that, we'll go into chemical reactions, which give states of matter. States of matter interact to make solutions. So that's a kind of an overview of what we're about to dig into. And we're going to start with atoms and basic structure and atomic theory, some of which is going to be familiar, some will not be familiar. Atomic theories. What's an atomic theory? An atomic theory is a model of the atom. Historically, 4 atomic models have evolved. John Dalton, who established the organizational format for studying chemistry, never defined an atom. He had ideas and drew symbolic graphic figures to say, okay, oxygen or nitrogen or mercury or whatever, but he did not have a designated understanding of what the structure is. In the latter part of the 19th century, really began the evolution of what we call the atomic structure and understanding of what they look like. And we call these 4 atomic models. The first one is what we call the Thomson raisin pudding model or plum pudding model. I'll list them all and then we'll go take each one, the basic concept of each one. The plum pudding model. Then there's a Rutherford shell model. The Bohr concentric ring model. And the Schrodinger quantum model, or modern quantum model. Now, I'm going to give you a brief idea of what each of these are, and then we will get into the more basic idea and concept. The Thomson model was visualized as a 3-dimensional sphere of positive charge And in that sphere were embedded electrons having negative charges. I'm trying to see, my graphics aren't all that great. And so that, in essence, was the Thompson model, and it was based upon opposites attract concept. The scientific community knew about negative particles or cathode rays and electrons. And they knew about positive particles and their nature, protons. They hadn't discovered the neutron as yet, but this is what led to the proposal of the raisin pudding model. This is based upon what we call the gold foil experiment. Very classic type of experiment. And the way it was set up is an alpha particle generator, a radioactive particle known as an alpha particle, which in essence is a helium nucleus without the electrons. And so this was a sample of an alpha generator. Was placed in a lead block, and so that the alpha particles would be directed at a very thin sheet of gold foil. Okay, and the idea was he started this with the objective of proving the Thomson model. If the structure of the atom was this sphere of positive charge, an alpha particle is a positive charged particle, is a helium nucleus, then what is expected is that this would just bounce off, and nothing else would happen. But when they ran the experiment, what they found was, and they put it into a photosensitive chamber. They found that 99.999% went through without touching anything. A small number of particles were reflected at obtuse angles, and a very, very, very small percentage were directed back at the source. What this led to was the shell model of the atom. In that, Rutherford concluded that the atom consists of a dense, indivisible nucleus, positively charged, surrounded by, let me draw 3 dimensions, a diffuse electron cloud. It looks like a sphere anyway. So when you're sending an alpha particle into that environment, which is plus 2, the alpha particle is, I don't know, 1,000 times, 2,000 times larger than the electron. And we'll learn more about this as we get deeper into this. It's going to go through here, through the environment of the atom, like a bullet through tissue paper. And it's not going to be affected very much at all unless it comes very close to the nucleus in here with the positive charge and is reflected off at obtuse angles. Or if there is a direct collision, it will kick it straight back. So that's where you came up with the dense, indivisible nucleus. Well, the ultimate outcome of this is that he was the first, and this is the test question right here, he was the first to define the two-part atom, the nucleus and electron cloud. Or to suggest. Electron cloud. Well, when we get over into the study of atomic theory in more detail, and in chapter 6 and 7, we'll add a lot more to this on the dimensions of what we call the average atom and relationship between the diameters and the nucleus and the atom, and on several factoids. That came about was the Bohr concentric ring model. This model of the atom is one that we recognize and use frequently in studies, and we see that as a nucleus surrounded by orbiting electrons. And they're called energy levels. Okay? And what the Bohr contingent visualized was that the electrons were orbiting the nucleus, much like planets, of course, orbit the sun. And so they had sophisticated numbers of electrons. They knew how to determine the number of electrons. The number of electrons, the max number of electrons per one of these orbitals is an easy calculation. These rings are called energy levels and are designated by a symbol N, whereas the first ring is N equal 1, N equal 2, and so forth. I stop at 7 because we have 7 rows on the periodic table, and that is significant. As you will see shortly, the largest element that we know of has only 7 rings on it. You can have an infinite number of rings theoretically, but we only know of elements that max out in 7 rings. But anyway, the max number of electrons they determined that can be placed in a specific energy level is 2n 2n squared. For example, this is n equal 1, you can put a maximum of 2 in there. And this would be 8, so yeah, that's right. No. How did I get this right? This should be 8, so that would be times 2. Now you can put but 8 in the second one. I've got something's not. Why am I getting this tangled? So you take n, you put it in here, and so that's the second energy level. 2 to the 4, 2 to 4 is 8. If you take the third energy level, 3 to 9, 2 to 9 is 18. You put into that one. 4 to 4 is 16, 32. Yeah. What do you do? 25, 50, and so forth on it. But that's just kind of a superfluous note here. Anyway, that they came up with the total number. It doesn't mean that it has that many in that ring or a ring. It has the capacity for holding that many electrons. And we'll look at that in great detail as we get into the electron configurations and how to put electrons in there. This was all based upon bright line spectra of hydrogen. And a bright line spectra of hydrogen, as I think I showed you the other day, if you look at a glowing cube of hydrogen gas, it'll break down into 4 principal colors: red, green, blue, and violet. If I can find my colors here. There we go. There's a red line, a green line, a blue line, and a purple one. Violet. Now, there actually is another one in here, but you can't see it, so the UV range. But at any rate, these said that electrons exist at certain distances from the nucleus. They do not exist between those distances in a nucleus. And so if you draw a parallel, say this is n equal 1, and this is n, let me put that up a little higher, n equal 2, n equal 3, n equal 4, n equal 5, and so forth. If you had an electron in that n equal 5, it can drop to n equal 4, or it could drop to n equal 3, drop down, and it gives off a very, what they call a discrete energy, discrete wavelength, as results in a discrete energy. That discrete energy is the distance orbital from the nucleus. And so hence they said, well, the electrons are living in very narrow bands and orbiting the nucleus, much like the planets orbit the sun. So without getting too complicated in here, That's the essence of the Bohr model. And it did lead to our modern concepts, and we use the Bohr model. Now, let me say this about theory. The idea of a theory is that no one theory is better than the other. The one you use is the best one defines the observations and concepts that you're working with. And so this led to identification of the concentric ring model. Let me do it like this. Orbitals, and they put like that. They called them n equal 1, 2, n equal 3, n equal 4, and up to wherever they're going. But anyway, that's the foundation I want to start with. And we will use this one in developing the specifics of atomic structure and so forth. Okay. Now, is the Schrodinger quantum model. The Schrodinger quantum model is based upon, and this is classic statement, the wave-particle duality of the electron. That is, the electron, under certain circumstances, behaves with wave characteristics as well as particle characteristics. So it has a dual character. Because electron demonstrates wave characteristics, this allows for application of statistical wave mechanics. To characterize the electron. When the field of mathematics called statistical wave mechanics is applied to the electron, it is called quantum mechanics. And that's how quantum mechanics was born. And quantum mechanics defines the electron in terms of quantum numbers. And we'll get into the great details of that at the appropriate time. But it led to, well, it was based upon what we call the Heisenberg uncertainty principle once it starts applying. So Heisenberg uncertainty says that the absolute position of the electron cannot be defined with absolute certainty. It can only be defined in terms of most probable location about the nucleus. ultimately led to is quantum numbers. And this led to electron configurations of elements. Now, some of you recognize these, say, as 1s2, 2s2, 2p6, 3s, 2, 3p6, and it goes on, and each element has its own designation like this, and we'll get into that at the appropriate time. But we find that the orbitals of the quantum concept might find part of the atom being a sphere, part of it being figure eights, and they're overlapping as shown here. And it gets quite involved, and then you have another one on the outside. So you can see it starts getting even more and more elaborate based upon the quantum model. And so in there, each electron has its own little window, we call the quantum window, and no other electron can occupy its quantum window, and I'll show you how that is determined. It's very easy. And that keeps all the electrons from bumping into one another. But at any rate, that's kind of a cross-section of the four models. Thomson, Rutherford, Bohr, and the Schrodinger. Now, what did you need out of this right now? Thomson model was the first proposed atomic structure. The Rutherford model was a two-part atom. The Bohr model was the concentric ring model, or the electrons lived at specific locations. Or energy levels. And the Schrodinger modern quantum model led to the current picture of the atom, what we think the atom is in reality looks like. Modern idea of whatever the atomic structure is. And we'll use primarily the Bohr model in talking about some of these issues. The atom, as we know it, consists of what we call fundamental particles. That is the proton, designated as shown, neutrons, designated, and electrons. The relationship between the protons and the neutrons and protons, what we say is approximately the same mass. We'll get into details in the future. But what I want you to keep in mind is the relative weight of the electron is 1/1832 of the neutron or proton. So it's a very, very small particle relative to the nuclear particles of proton and neutron. In structure, the atom is two parts. I'm not telling you anything you probably already know. Nucleus and electron cloud, which holds the electrons at specific energy levels. And in that nucleus, we have the protons and the neutrons, and the electron cloud contains the electrons. And so we've already identified the nucleus as a positive entity with a certain number of protons that is responsible for the positive charge, but it also has so many neutrons. And around it, we have the energy levels, n equal 1, 2, 3, 4, 5, 6, and 7, which is the maximum number of rings that we know of in the contact. And again, the max number is 2n squared for the max number of electrons that can be put into a given energy level. Now, having said that, what we want to do is look at the periodic table, and with the base data that's here, define how many neutrons, protons, and electrons a given element has. So when you look into the periodic table for a given element, you'll see two primary numbers. One is a larger number and then a smaller number. The smaller number is called the atomic number, and the larger number is the atomic mass. This is called the element block. So if we pick one, silicon, for example, it'll have a symbol Si. 28.085, isn't that 28.085, and it's number 14. Number 14 in here, you'll notice that all of the blocks are numbered sequentially, 1 to 103, 106 on this. Anyway, I need to fill in the rest of the elements. But this 14 is called the atomic number of the element, and is a designation of the number of protons. So you pick any element in there. Cadmium, number 48, has 48 protons. Nitrogen has 7 protons. Now the importance of this is you change the number of protons, you change the element. That's long and short of that. So if you knock out a proton, you have something else other than whatever you started with. Anyway, the atomic mass is, well, we'll talk about it in two contexts here in a little bit. The atomic mass is the protons and neutron mass combined. The number of protons plus the number of neutrons that's in the nucleus. Now, we'll get into the numbers of electrons shortly in terms of neutral ions, things of that nature. But what we want to do is do the protons and neutrons for any given element. Now, the designation of an element like this is written. Now, you'll see different arrangements in the element block. Some periodic tables will have the atomic mass at the top, atomic number at the bottom of the block, and they'll have all kinds of other stuff around it. But we're starting with just this basic generic layout and working up from there. Now, designating this, the symbology for this, can be written as one of two ways. Now, since all silicon, all of them, regardless of their isotopes, and we'll talk about that, we'll have 14 protons. So there's no point in designating that in here. And so what is done frequently is they'll simply write Si28, which is a mass number. And the mass numbers do change because the neutron numbers change. But there's no need to put a designation for the proton in some cases. And it's used because it's always going to have 14. You'll get out. Another designation is when you do put the designation for protons in, you want big number over little number. That's the simplest memory device I can give you. That is, round this mass number to the nearest whole number, put it as a superscript, and subscript 14, like that. Big number over little number. Now, since this is always the number of protons, and this is always the number of protons plus neutrons, you can take the little number, subtract it from the big number, and get the number of neutrons. So there'll be 14 neutrons in this designation. And that's how simple it is. So for any element on here, you can get the number of protons and neutrons just by simply taking the big number, round the mass to the nearest whole number, and subtract the atomic number, and that's your number of neutrons. So we'll throw in a little table here that I usually construct. I say carbon, okay, and carbon is designated 12 and 6. So the number of protons and the number of neutrons. We'll back up a little bit. Protons and neutrons. We'll go this. Well, if this is the atomic number, you got 6 protons, and 12 minus 6 is 6 neutrons. That's good. That's it. And we'll talk about the electrons in a little bit, so bear with me. Okay, if you go to calcium, I'm just picking them at random. You'll see it is 40 mass number, and 20 is the atomic number. And so we have 20 protons, and 40 minus 20, 20 neutrons. And nickel is 59, 28. So we have 28 protons and 31 neutrons. So you can go all over the chart and designate the numbers of neutrons and protons all over and over and over in this context. And what about the electrons out here? Now, electron numbers are designated relative to neutral, cations, or anions. And what we want to do to begin with is talk about the neutral element. So if electron is negatively charged and proton is positively charged, we want to cancel those out for a neutrality or neutral element. And so if you have 6 protons, you need to have 6 electrons in the structure in order to cancel it out, and that's a neutral. Now, elements do gain and lose electrons in the process of chemistry, and so but those produce ions, which we will get to shortly. Okay, here you got 20 protons, so you have 20 electrons. Here's 28 protons. You're going to have 28 electrons, and these are neutral. Now, again, some elements gain electrons, some elements lose electrons, and we'll talk about that at the appropriate time. But this is how you determine the neutrons, protons, and electrons. Remember, question comes up, which of the following is the composition of the nucleus? Don't pick the one that's got neutrons, protons, and electrons. Electrons are in the electron orbitals around there, so just a hint for the quiz tomorrow. Anyway. Okay, now we get into the variations of atomic. Okay, when we talk about variations in atomic structure, we separate them into nuclear variations and electronic variations. Nuclear variations would be the structure for a structure and lead to variations in the numbers of neutrons. And these are referred to as isotopes. So an isotope or isotopes are a collection of the same element, all having different weights because of the different numbers of neutrons. They all have the same atomic number because they have to, or they would be different elements. And we'll look at that in a second. Electronic variations is due to gains and loss of electrons at the valence level. if we use the Bohr model and say an element has 4 rings, the first 3 rings from the nucleus out is called the core structure. And the outer ring, as many of you already know, is the valence level of the element. This is where all chemistry takes place. The core structure is very stable and typically resists any changes in its structure. So when we talk about all chemistry takes place at the valence level, the valence is a gain or loss of electrons in chemical process. And that constitutes the fundamental nature of the chemical reaction, is that one element loses electrons to another, or another element gains electrons from another element. Now, we want to work problems that are associated with isotopes and work problems associated with variations in electron. Isotopes refer to a set of elements all having the same atomic number. But different atomic masses. The variation in atomic mass is, of course, due to the variation in the number of neutrons in the nucleus. You cannot change the number of protons in this collection of elements because you change the element. So, okay, there are 2 isotopes of chlorine. Now, we have chlorine 35 and chlorine 37. Chlorine being atomic number 17. Well, both of them have 17 protons. Now, 2 numbers are very important here. What we call the isotopic mass. And these are expressed in a relative term called atomic mass units. There is what we call the rest mass of the element, which is, say, something like times 10 to the minus 15th of a kilogram. But when we talk about atomic mass units, we talk about a relative mass. That's relative to, say, carbon 12. It's so many times heavier or so many times lighter than the carbon 12, and that's how it's designated. We'll show you a little more about that as we go along. Well, the relative atomic mass for chlorine 35 is given to be 14.96885. Okay, and the atomic mass of chlorine 37 is 36.96590. Now, this is a mixture of particles, all having the same atomic number, but different atomic mass, and they exist in that mix in certain fractional quantities. So we call it the fractional abundance. Fractional abundance of chlorine 35 is 0.75771, and the fractional abundance of 37 is 24229. Now you express these in percentage, but if you multiply them by 100, and what it means is that 75.771% of all of the chlorine elements in the universe are this form, chlorine 35. And 24.229% of all the elements of chlorine in the universe are of the form chlorine 37. Now, these, if you're adding percentages together, it would be 100%. But this should add up to 1.000, so as a designation, because it represents 100% of the mixture. At any rate, I'll get rid of that. Now, with this data, that's what's given in a problem. The problem that you need to answer, or the question you need to answer, what is the weight average of the chlorine isotopes? Or determine what the test will say. The weight average atomic mass of chlorine. So that's the problem you have to learn to answer. There's a pretty straightforward calculation in this. You take the atomic mass, isotopic mass, times the fractional abundance, and you'll get a weight average contribution for 35. And you take the weight average of the isotopic mass of chlorine 37 times its fractional abundance, and you get the weight average contribution of chlorine 37. So let's do that right here, 35. So we'll have 34.96885 times 0.75771, and then we'll have contribution from chlorine 37, 36.96590 times 0.24229. So those are the total weight average contribution. It's 45.4527. Around that to 35.453. If you want to. The total weight average contribution of all the isotopes is the number put on the periodic table, the mass weight. So any number on the periodic table is a weighted average of all the isotopes of that given element, and it's computed in the same format. And that's what I was going to show you real quickly here. And right here is when you look at chlorine, 35.453. Well, you take 35.4527. That rounds to 45.453. So you see, that's how you get the weighted average of the atomic weight of those elements on the periodic table. And this is pretty straightforward calculation. There are some variations in this calculation, and in some problems they'll give you the weighted average total, and then ask you what the isotopic weight is. In other words, you'd have to set it up as a combination. We'll work some problems with that as we go along, but I want to get, we're out of time. Okay. Anyway.